with us today. He's written several things on in the area of philosophy of astrobiology. He's based at the University of Nevada in the Department of Philosophy, but has also worked in biochemistry. And I'll pass over to Carlos, who's going to talk about philosophical issues at the ends of life. Go ahead.
Thank you all. Thank you, Peter, and thank you all for coming here. I really appreciate the invitation. I'm actually going to be in the UK sometime in August, so anytime that any questions that you have, hopefully you write them down and we can chat over them over a beer or coffee or whatever when I'm there. I'm planning kind of a big European tour at the beginning of my sabbatical, which will relate to this talk quite a bit, actually. Okay, so I'm speaking about the philosophical issues at the ends of life, and I just thought that I'd start off by telling you what our agenda is today, what we're going to talk about. I'm going to start off with some background. I'm going to give you motivation and contextualization of what we're talking about, both personally and for you, so you can see why I'm interested in this, and hopefully so you can also be interested in this yourself. Then we're going to talk about the Fermi Paradox. We're going to talk about some potential solutions to it, which aren't really the driving force for me. What I really hope that you take away from this is the idea of Fermi as an analogy, which has been said before, but I think that there's some deeper implications for the future of life and the ends of life. Okay, so motivation. And please, by the way, feel free to stop me if there's ever something that I said that wasn't clear, or if you have any questions that you want to just raise. Otherwise, we can leave the discussion for Q&A. So why am I interested in this? I sometimes find this happens to me in my philosophical career, that I am not interested in a topic for whatever reason. I have like this knee-jerk response to it, this knee-jerk approach, and I, for whatever reason, just don't want to talk about it. And then somebody asks me and really presses me on it. And by the time I'm answering them, I actually get myself interested in the topic. So this sort of is what happened here. It goes back to Lucas Mix, who I believe is there. I don't see him, but inviting me to this session on the future of life, on this idea that astrobiology is supposed to be the study of the origins, evolution, and distribution of the future of life in the universe. So astrobiologists purport to study the future, but they don't, right? They rarely do anyway. And it was interesting. I don't think that I did the best in that session, but I've been thinking about it for the past 8 or 9 months, and trying to wrap my head around why I think thinking about the future, and in particular thinking about the ends of life, is particularly interesting. I think there's a couple of reasons. One, if we are interested in life, either here on Earth or elsewhere, we might be interested in the paths life might take. We might be interested in its origins, which people have done a lot of research on, including myself and including some of the people in this room. We might be interested in what life must be like. We might be interested in how life could possibly be like. We might be interested also in how it ends. I think that's the next logical step of the path, right? How it originates, what it is, what affects it, how it might end. And also, I'm not. I don't believe that this conceptual space is very well mapped out, which is exactly the place for philosophy to do some good. Philosophy is really good at seeing how complex ideas relate to each other, and so to the extent that I can offer something, I think that's where me and other people who are interested in these questions can offer their piece. And lastly, this is foreshadowing the end of the talk. Milan Cirkovic says that when we think about life elsewhere, it really is sort of a magic mirror to the future of our species. It kind of, life elsewhere addresses all of the questions that we're talking about with respect to the origins, distribution, and nature of life, and the ends of life. And so it's interesting to think about what we might find and what we might not find, insofar as it might speak to us, but also just because it's interesting. So over the next year, I'm going to be on sabbatical from July to July, and I'm hoping to spend that time writing this monograph on the philosophy of astrobiology. I've written on a lot of the topics related to what I'm hoping to write about in this monograph. What is life? I have a paper in Synthèse, which some people here know about. I also just wrote the Stanford Encyclopedia entry for that. How does life originate? The questions there, I've written something on that. What can we expect life to be like? My dissertation was on universal biology, and I've spent some time wrestling with those questions. I haven't so much spent time wrestling with where are we looking, but I recently wrote something on will we ever know if we're right? And then this talk will be hopefully the end, or at least part of the end chapter. So this is part of a bigger project. Hopefully you can give me ideas, suggestions, directions on what you like about it, what you don't, what I should add, what I shouldn't, in order to flesh out this project a little bit more. In that last chapter, I'm hoping to talk about issues at the ends of life, and I think some of the philosophical issues here are going to be somewhat mirrored to the issues at the origins of life, which I've written about in other work. First, philosophers, we're really good at definitional clarity, or at least that's what we try to do. Somebody told me once that the correct answer to every scientific question is, it depends. And I think the correct answer to every philosophical question is, well, what did you mean by that question? So I think some clarity on ends, on time frames, on what the future we're talking about is. Also, questions of necessity, universality, convergence, contingency about the future of life. And then questions about the sources of our information and how they interact with each other. And I think that a lot of the various sources that we use to try to infer questions about the nature of life can be used to apply to the future of life and then to the ends of life. But they have different epistemic, different conceptual grounding. Right? So how they relate to each other is not intuitively obvious. And in fact, some fields might use different assumptions that might conflict or be in potential inconsistency with the assumptions made by other fields. And lastly, of course, the ethical questions, right? What should we do? The normative questions. Okay, so hopefully that's enough background, enough prologue. We're going to get started on the Fermi Paradox, which I think will sort of be an interesting lens by which to think about the future of life and potential ends of life. Fermi Paradox is one of those where I was, again, desperately uninterested in it for a long time. And the more I try to think about why I wasn't interested in it, the more interesting it became. So hopefully I'll be able to bring you along. I have the fervor, the passion of the converted here. David Brin's quote spoke to me deeply for a long time, and still does, actually. Okay, so there's many formulations of the Drake equation. This is a version of the A form that it essentially collapses all of the questions into a couple of key variables. So we're asking, how many technological species have ever lived. In the next slide, I might actually take out the term technological. I might talk about life worlds. Well, maybe not the next slide, that slide after that. But that could be composed of some astronomical questions, such as the number of planets in habitable zones, but also some biological questions, which are the ones that we are less comfortable with, such as the number of times life has evolved or produced energy-intensive technology or other effects. There's this really great paper by Craig and Sullivan, where they tried to put some empirical constraints now that we have some answers to at least some of the astronomical questions. And depending on the frame of reference that you use and what you are paying attention to, you get slightly different numbers, and they have the big number that life must, unless it's 1 in 10 followed by 24 zeros, life must have occurred somewhere in the universe, but really somewhere in the galaxy, 1 in 50 billion-ish. So unless life is that rare, it should have occurred more than once, more than here. Which directly leads to the Fermi Paradox of where is everyone, right? There's a couple of formulations of the Fermi Paradox. I think in Milan Cvetković's book, he talks about the strong Fermi Paradox, the lack of any intentional activities or manifestations or traces of extraterrestrial civilizations in our past light cone is incompatible with the multiplicity of extraterrestrial civilizations and our conventional assumptions about their capacities. All of the emphases are mine. I don't know why I emphasized about. It's funny. You might formulate a stronger version, or maybe the strongest version of this, about the lack of any evidence for life, right? It's not just that we're not finding technological civilizations with SETI, it's that we're not finding anything at all. Now, a lot of that might be because we haven't been looked, right? The JWST was only launched recently, and we're only trying to look for biosignatures. Well, we've only been looking for biosignatures here in the solar system, and we're only starting now to look for biosignatures elsewhere. But the strongest formulation, so it might be too early to wonder where is everybody until we get more data. But until we get more data, actually, the more data we collect, and the fewer results there are, the stronger the strongest formulation of the Fermi Paradox is. Milan in his book talks about the basic assumptions. There's some very basic assumptions in the Fermi Paradox, and if you challenge any one of them, you get a cluster of answers, purported answers to it. So first, realism. Science gets to the real world out there, and it operates much in the way that contemporary science says it does. So there is a great silence. We genuinely haven't detected life elsewhere. I have a cousin that believes that reptilians are controlling all of the leaders of the world, and they spend some time hanging out in the hollow earth. I think he's wrong. I hope you all think he's wrong. But if he's right, then we can we can explain away the Fermi Paradox. Okay, Copernicanism, there's nothing special about us or Earth. Gradualism, don't really like some of these terms. There's nothing special about here and now, but then he complained that there was no ism for the economic assumptions, and I thought, well, there's economists, we can attach an ism to them. Civilizations are like us and believe it is rational to spend resources on interstellar travel or communication. So you can get a cluster of potential responses to them. Other people have divided the potential responses differently. In particular, Stephen Webb's talked about the 3 major divisions. They're already here, they don't exist either now or anymore, and we haven't found them yet, which I think actually maps on fairly well to Cvetković's categorization, right? So if they actually are already here, if my cousin is right, if people that claim to see UFOs are right, then we have some pretty direct evidence. It's just hiding from us. I remember the first time I gave a talk, I think at Library of Congress, one of the first questions was, why aren't any of you investigating the good UFO sightings? And I thought, I don't know. I don't think there's any UFO sightings, but I haven't done a lot of the research, so who knows? Okay, fair enough. They don't exist either at all or anymore, so maybe Earth really is super duper special. Maybe you needed to have a moon of a certain size and Jupiter of a certain size, and you needed to have circumstances of the right form in order for life to form, and it just doesn't happen elsewhere. And so it's not strange that we don't see life elsewhere. Or maybe it does exist, but it goes extinct very quickly. You might still expect to see some remnants, right? To either see, in the case of technological species, you might still expect to see remnant radio signals, some evidence of technology. In the case of just regular life, you might still expect to see some biosignatures, but I know a lot other people have spent more time wrestling with questions of biosignatures and diagnostic biosignatures than I have. So maybe we can talk about that later. And then we haven't found them yet. Maybe we're not looking in the right places. Maybe they don't want to be found. Maybe, who knows? Maybe we just have only looked for a cup of water in the Pacific, right? That's the analogy people say. Our search so far has only been the equivalent of going to the Pacific with a cup of water, or a cup, taking out some water and saying, I don't see any fish here, therefore there are no fish. Okay, cool. Chitkovich also spends some time considering all of the potential solutions, and he grades them. He gives all of the potential answers and grades. I summed up a lot of these grades, and we'll talk about some of these in particular in a little bit, but essentially the one that I was a little bit most dismissive of early on, he gives on average lots of Fs to these. Maybe Earth being particular, like a special case. There's a couple of answers that he likes. There's a couple of here that I like too, which I'll talk about in a little bit. But on average, they're not great. So this is the standard American rating system where A is either a 9 or a 10, or 90 to 100%. B is 80 to 89%. C is 70 to 79%. D is 60 to 69%, and F is anything below that. So even in the rare earth, there's a couple that get pretty good grades, but most of them aren't grades. Great filter, there's a lot more suggestions here, but on average, more is not better. So, and then he considers a bunch of other possibilities that we might be just biased in certain ways, and again, scores are roughly the same. So his final wrap up, he talks about these 3 different clusters that he thinks actually fit together, these 3 kinds of explanations that really work together, work well. So first, the Gaian window, great filter, and the giga year of living dangerously, which in short and in order are, there's a specific window of time in which complex life can evolve. At least one step toward complex detectable life is extremely rare. The galaxy is more dangerous than it seems. Maybe there's lots of supernovae throughout, and they just wipe out origins before they come up. Maybe we just got lucky, we have tectonic plates and those really matter. Or maybe we just needed to be around at a 3rd generation of star systems where we get some complex, some heavier elements to make more complex chemistry. Okay, the second one being deadly probes, resource exhaustion and sustainability. all get B's, and and in short, these are, and in order. Intelligent civilizations destroy new ones. Sometimes this is called the dark forest hypothesis. Empires collapse, so any galactic civilization would collapse. And then the last one, sustainability, which goes back to Jacob Hockmistra and colleagues. Exploring is extremely difficult, so it doesn't happen often. I'll talk about that shortly. And then the last one, the new cosmogony, transcendence, transcension, living on the rim, and the great old ones. The earliest civilizations are indistinguishable from normal physics and have transcended biology or technology as we know it, and exist near the limits of galaxies or black holes and are currently inactive. I'm not sure I understand that last one. My own biases and I just have an aversion to more science fiction scenarios. So I'm not really going to spend a lot of time talking about this last one. But if you want to come back to this last cluster that Yurkovich thinks is worth considering, I'd be glad to talk about it. Okay. So we'll talk about the first cluster, the Gaian window, early great filter, giga-year of living dangerously. That's that. There's a specific window of time, but might be extremely rare, and the galaxy is more dangerous. So the great filter. I spent some time teaching climate change, and I am constantly stressing my students out because I think it's a much harder, much worse problem than a lot of people are aware of and actively consider. One of the things I talk about is Jared Diamond's book Collapse, in which he talks about the various things that have led to many civilizations collapsing, and how there's some special new possibilities, new risks, new terrors to be afraid of, including climate change and toxins and other things. And the idea is there's these 12 risks. You might come up with a different list. We might not like some of these or want to add more. But the quote that I really love of his is, it's not that one of them is worse than the others or that you should try to avoid one more than the others. If there are 12 bullets firing at you, it's not enough to dodge 11. You have to dodge all of them. And the idea being there's many, many bullets heading towards human civilization and perhaps to life in general on Earth, but I'll talk about that shortly. Okay. There's this really cool paper. Very few papers in climate science actually spend some time talking about worst case scenarios in the deep, deep future. We tend to stop at around 1 or 0.5 or 2 degrees centigrade, maybe at the end of the century, given current consumption or making some assumptions about what we're going to do in the future. This one paper does actually spend some time getting into the, I realize I did not include this source, but it's easy enough to find. It really goes into what the world might be like in 2500, given some of the more extreme climate scenarios. And in short, it's really bad. The Amazon would become barren, and in some parts of the Middle East and Northern Africa and Southern Asia, you might not be able to go outside during the summer without intense protection. So that's climate change, but there's other things that might cause us to be afraid. There's great filters. And I want to divide these into a couple of categories. One, every creature dies, all humans die. Or if you want to think that maybe we're not that special and life would evolve intelligence and technology after us, maybe 100% of all life dies. Somebody, a geologist once told me, and I don't know how true this is, that if velociraptors had built skyscrapers, we wouldn't know it. I should look that up, a trusted source told me. So, okay. The second possibility is fewer than 100% die. It's fewer than, it's less than total devastation. And the third possibility is we don't know what would happen, right? I think this is probably a nice conceptual distinction we can all accept, hopefully. Now, extinction is inevitable. Every species that has existed up until very recently has gone extinct. Some of those have speciated. I cut out some slides on speciation because I don't think that they're actually that interesting or relevant to my talk, but we can talk about that if you want as well. So whether we go extinct in the next 500 years or in the next 5 million years, those differences matter with respect to a lot of things that we're going to be talking, that we care about with respect to detecting life elsewhere. And the fear is that maybe a lot of life in other parts of the universe might have gone extinct before it could be detectable, and it might have suffered from some of these risks. There's this book by Toby Ord, The Precipice, that came out maybe last year, estimating extinction probabilities. And he has the non-human causes and then the human causes, the natural risks and the anthropogenic risks. And the metric that he uses is what are the odds that humans will be extinct in the next century? And the total natural risks are about 1 in 10,000. But you'll note that most of those, perhaps I should have included asteroids and comets as being 100% devastation, but it really depends on the size of the asteroids and comets. Super volcanoes, pandemics, the human causes, those are much, much harder to estimate, and we might all have different estimations here than he does. But he says it's about 1 in 6 that we go extinct in the next century. That seems a bit high for me, but okay, we'll take that. So, so that's in short the great filter, right? The fear is that there's a lot of things that could cause extinction. Maybe the stellar explosions is something that we should particularly be wary about, because in the solution to the Fermi Paradox that Trutkovich talks about, the giga-year of living dangerously, maybe that just happens a lot more often than we think about, and that would itself explain why we don't see anything. Okay, now I'm going to talk about the second and last, well, the second cluster now, the hermit hypothesis. And actually, this will, I'm going to start off with where the last talk left off. So in the last video where Lucas chatted with you all, the last talk, there's one Q&A, one question left in YouTube, and Lucas's answer was kind of my answer, right? Why would anybody want to conquer the galaxy? I didn't know that we were supposed to. There's supposed to be this assumption that that is a goal for any intelligent species. And you factor in some Malthusian ideas of exponential growth and limited resources, but then add in a bunch of advanced technology, and you would think, perhaps the advocates say, that once we run out of iridium or any of these other rare earth metals, or once we run out of the things that we want here in the solar system, we were going to need to go elsewhere to get it. But that, I think that underscores how vast the differences are, or the distances are between star systems. The nearest system being 4 and change light years is about 6 trillion miles. Does not seem like you could do that in a weekend. And I think that there's reasons to think that cultural, even biological, actually, even evolutionary pressures might speak against these long-term projects. I'm going to show you a video of the Great Wall of China, the longest human project. It took about 2,000 years from beginning to end to build. There were many stops and starts, many different dynasties built it. And one of the things that I want you to notice about that is at every point, the wall was useful at keeping barbarians at bay, at keeping the Mongols at bay. And it took a good chunk of the entire existence of the Chinese civilization, which is one of the longest lived civilizations, to do it. But there were many periods of revolution, many different dynasties throughout. And that's true for all of the longest lived civilizations. There are some projects that are a bit more frivolous, but those tend to take less time than a couple of thousand years. And so when we're talking about actually traveling to nearby star systems, we're talking about distances that are so huge that it would take tens of thousands of years to get there at current speeds. Maybe we can speed that up, but still it would require choices made by current civilization, or maybe us in the slight future, to decide that that is a viable plan, and to invest lots and lots and lots of resources to doing that. And then once we get there, we don't actually arrive on a livable planet. I mean, the environment of Earth and humans and life on Earth co-evolved. You would need to actually make lots of changes to anywhere you would get to actually make it habitable in any sense that we care about. You'd end up spending, you'd trade a planet for a ship. And so even if you think that exploring is a worthwhile project, based on what we know about physics, unless we find a way to control wormholes or something, which the fact that there are no galactic civilizations itself suggests that we might not ever be able to do, unless we start finding them, then there's really no incentive to just spend the rest of your life and the rest of your children's lives, et cetera, on a ship traveling. Unless, of course, you get the combination of the two, the great filter, and then we have to leave for whatever reason. But we'll talk about that more later. So I'm a member, co-founder of an organization called SOCIA, a Society for Social and Conceptual Issues in Astrobiology. We're having a meeting in Sweden in 2024, if you'd all like to go. And at the penultimate SOCIA, there was this talk that stayed with me, and it really just changed how I think about a lot of things. And it was the answer to this question about leaving the solar system. And I mean, I know we've sent probes, but the answer was in mass. Will humanity ever leave in mass? And the short answer is no. But the long answer is, we know the particle physics, we know the physics that we need to be able to send big ships long distances, big crafts long distances. And essentially, all of the various particles that we could use, all of the various elements that we could use, many of them are either very rare or have an extra neutron that ends up being shot off whenever we cause a fusion reaction, which means that it would absorb the majority of the energy, which means that it would actually be a bad source of fuel. And if you look through the early part of the periodic table, you find that we actually don't have a lot of the elements that we need, or the ones that we do won't work. And the only one that actually is pretty good would be boron. That would actually be a fairly good rocket fuel. Problematically, we're using it for soap, and we're going to run out of boron in the next generation. We're using it for borax and other things. So we won't leave the solar system, is the conclusion. At least not us as in mass, as humans. Of course, this doesn't work for non-biological beings. Maybe, I mean, we sent Voyager. It hasn't left the Oort cloud yet, but we sent it far away. Maybe we could send ChatGPT next, you know, see what it has to say and what it discovers. But that also, none of this is going to speak to signals of any life, intelligent or not. And that's really what the strongest version of the Fermi Paradox is. We keep getting distracted, and I got distracted in this last thing, considering why we haven't seen technology. We haven't seen a lot of stuff. So, okay. Patchwork solutions. I think Stephen Webb and other people have been convinced that you can just combine a lot of the potential solutions and they might all work. They all make things less and less likely. But Mark Walker, a friend of mine at New Mexico State University, has pointed out to me that given the vastness of the universe, probabilistic solutions aren't enough. We need a law-like solution. We need something that explains why we never see technological civilizations, why we never see life. And again, this might not be the strongest version of the Fermi Paradox, might not be that captivating right now, but if JWST doesn't find things more and more, the rest as we move forward in our lives, the motivation for it gets stronger and stronger. So some of the solutions I offered about motivational tensions and maybe some barriers, maybe great filters might work, but only if they always worked, if they always put things in tension with each other. I might think about canalization, which is something that happens in development to make an organism resistant to environmental perturbations so that you develop in normal ways. You might think about an analogy to this applying with life in general. So even if there is an infinite universe, even if there's infinite iterations, infinite possibilities to try, there might just be some options that just don't happen. And they can't happen because they get channeled, they get canalized into particular solutions, right? Given infinite time, you still won't have zebras evolving machine guns, but you might have any other number of creatures evolving. So maybe the same is true for interstellar travel, communication, survival. Maybe some of the issues that we've been talking about really explain in a way that might be as law-like as we need for a solution to the Fermi Paradox. You don't need it to be, well, it becomes law-like if, even given infinite options, if you always end up in the same paths. Okay, so one more slide after this, we'll talk about the Fermi future. So I think about this quote a lot. If we are going to colonize the galaxy, why have they not already done so? I mean, I don't think we will, is the answer. Okay. But what I want this to all be pointing toward, and hopefully I'll connect the dots a little bit more in the chapter that I'm writing, is using Fermi as a guide to the philosophy of ends. If you recall at the beginning, I said I gave some philosophical issues with respect to the ends of life that might be interesting. One was definitional questions, which I don't want to spend more time talking about, but that is a thing that philosophers do talk about. Another is the contingency, convergence, universality, necessity, all of these terms that mean slightly different things, which we can talk about the nuances if you really want to get nerdy about it. But how certain are the outcomes that we expect? So any solution to the Fermi paradox, if it captures life elsewhere in the universe should tell us something about the future of our own civilization, our own species, our own biosphere. Now there's a bunch of new approaches with the JWST that are really exciting, and we're sending the Dragonfly mission up to Titan pretty soon, and we're going to Europa. We're going to all of the places that we're most excited about. So maybe these will help alleviate some of these issues and maybe obviate all of them. But how can we know? I mean, the more we explore the Fermi Paradox, the more we see what we can possibly know. And in the absence of any information whatsoever, that's when we can start drawing different conclusions. And then lastly, what should we do? Well, I think I've become convinced, I don't know if I've convinced you, that we should not expect to leave the solar system and plan accordingly. But also, unless there's discovery at some point in the near future, maybe we might also not leave signs of our civilization for future discovery, and how we ought to engage and wrestle with that question is something to take seriously. Okay, and with that, I'd like to thank you all for your attention. I'm really excited about talking to you over Q&A and over coffee or something when I go visit in a couple of months. Thank you. Any questions?
Thank you very much. So if there are some questions in the chat or in the room, just help yourself. I think I saw Paul River already had a question in the chat.
Oh, there's another reference for calculations addressing the Fermi Paradox and Drake equation. Oh, excellent. Thank you. That's very helpful. Seems like a test for the robots. Yeah, maybe exploring might be. I think that